What do you think? All right, so I really am happy to host Karina here, Karina van Shuckman. I met Karina about 2 years ago, I think, when we were authoring some section for the IPCC, and it was really a pleasure to work with her. And as I told you, send you a quote from Jim Hansen that says, if I read the quote over here, Karina van Shuckman has become perhaps the world's leading expert in monitoring Earth's energy imbalance, in some sense analogous to death-killing monitoring atmospheric CO2. That's a huge compliment, I think, because the competitors are really tough. I know them. So so I'm really glad that we had the opportunity to invite Karina. I actually, all my meeting with her were through Zoom. We were supposed to meet in Toulouse, where she is. She's working for Mercator Ocean Center, or did I pronounce it right? Which I understand from her is a public supported research institute. Karina got her PhD at Gilmar, and now for the last 15 years, she is in Toulouse in France. And without further ado, I will give her the stage here.
Thank you very much for the introduction. And yeah, and thank you very much for the invitation. And I'm happy that I can provide some insights on the Earth's energy imbalance, with particular providing some general overview on the current status of knowledge and advancements, and also on the remaining challenges. And please do not hesitate to interrupt me for any questions or keep them for the end. So just start with a general view is on the Earth energy budget. So the Earth energy budget is determined by the main flows of energy into and out of the Earth system. So particularly deriving from this knowledge is that the state, the variability, and the change of the climate are to a large extent driven by the energy transfer between the different components of the Earth system, like the ocean, the atmosphere, the cryosphere, and the land, for example. And the energy flows, they then alter clouds and weather, and also external and internal climate forcing. They can change and alter the Earth's energy balance at the top of the atmosphere on different timescales. And this can happen at periods of days, but also up to periods of several decades. So given this complexity and given those importance of the Earth's energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. So how can the Earth's energy balance be changed and how is it defined? So the perturbations of the equilibrium Earth's energy budget arise from an internal or an external climate variations, and they can create a positive or a negative Earth energy imbalance at the top of the atmosphere. Like positive, for example, that the amount of incoming solar radiation is larger than the amount of emitted infrared radiation, leading to an accumulation of heat in the climate system, or vice versa for a negative Earth energy imbalance. And then it's manifested as a radiative flux imbalance at the top of the atmosphere. So what is the current status today, and how can the variations occur? So the variations of the Earth's energy budget are determined on how energy flows govern the climate response to radiative forcing. So these include the changes in atmospheric composition and the land use. So this on the left-hand side, you can see the assessed results from chapter 2 of the last R6 report. So these include, for example, for the atmospheric composition and the land use, anthropogenic greenhouse gas emissions and emissions of aerosols and the precursors, and affect climate through perturbations to Earth's top of the atmosphere energy budget. And also variations are delivered by how the climate system responds to a given forcing, so the equivalent climate sensitivity and the transient climate responses, and those are determined by climate feedbacks, and those in turn are associated with physical, biogeochemical, and also biophysical processes. So again, reflecting the complexity and the importance is an understanding of the changes in the Earth's energy flows helps understanding the main physical processes driving climate variability and also climate change. So how can those changes be occurred? How can those changes be forced? So again, I keep with this presentation from chapter 2 on the observed changes on the so-called effective radiative forcing. We can see here different forcing agents, that's climate forcing, that's greenhouse gases, including carbon dioxide, but also natural variability, like the volcanic here shown in green, or the solar radiation shown here in dark yellow. And on the right-hand side, you can see an example of a time series for the Earth's energy imbalance, where you can see, for example, huge peaks occurred during times when there had been manifested in strong volcanic eruptions in the 80s and the 90s, for example. So what are those changes? So there are changes which can be forced at different timescales. Either they occur at sub-season to decadal timescales, and those are linked to climate variability, which can lead to either positive or negative Earth energy imbalance, linked, for example, for an new southern oscillation or Pacific decadal oscillation, or large volcanic eruptions, which can lead to a negative temporal Earth energy imbalance, or for decadal and longer timescales, like changes in solar output, variations leading to negative or positive change, Milankovitch cycle, also both direction, and anthropogenic change, which is leading to a positive Earth energy imbalance. And this is what we are observing today. Today, we are in a current status, as assessed, for example, in the last IPCC report, and stating that the human-caused net positive radiative forcing causes an accumulation of additional heat, energy in the climate system. So estimates of the net cumulative energy change are shown here for the period since industrialization in the 70s and up to 2018 here. On the left-hand side, you can see again an accumulated diagram on the radiative forcing as expressed here as energy change, and related to this, the heat inventory on the right-hand side, where you can see on where this accumulated heat is stored in the Earth system. But I'm coming back to the heat inventory later. This is also another manifestation on the results obtained, currently available in literature, on what is the current status of the Earth's energy imbalance today. So also here is a clear indication that the Earth is out of balance, and that this is in a positive way, so that we have a positive Earth energy imbalance at the top of the atmosphere, leading to an accumulation of heat in the Earth system. These are published results, a schematic evolution, and you can see here in different colors. On the lower hand, you can see a list of different publications which have done independent estimates of over different periods of the Earth energy imbalance. And you can see here in yellow are these values, which I will discuss later in more detail, which is an international assessment study published last year under TICOS, WMO TICOS, and which will be updated next year. And in green one are the most recent estimates. So what you can see are overall increment, but what you can also see is an overall agreement that there is an increase in the rate of change of the Earth's energy imbalance over time, and meaning that we are leading to an agreement that the Earth's energy imbalance seems to increase over the past decade. So further on this, so this is so what is here the major point in terms of the Earth's energy imbalance, so leading to accumulation in the Earth system, and this heat is redistributed or stored in the different Earth system components. So here are the numbers which had been estimated for the recent years since the 1970s, and so it's the ocean heat uptake is by far the largest contributor, followed by land heating, melting of ice, and warming of the atmosphere. So I've provided here some numbers. You can see that these estimates are still a bit varying depending on which time period you are, but the major contributor is the ocean. So there's over agreement, and there's then land and cryosphere, land with about 5%, cryosphere with about 3%, and 1% for the atmosphere. For comparison, you have also here the most recent estimates assessed from during R6. So how can we measure, how can we estimate the Earth's energy imbalance? So I provide here an overview of 4 different methodologies which could theoretically be used and which are in use and which can help to further unravel open questions on the Earth's energy imbalance. So the first is the direct measurement of using remote sensing technique. So there's this NASA series program in the US, which is providing information on the net flux at the top of the atmosphere, TOA, which is the TOA here. Then there's an estimate which can be derived by providing an inventory of the Earth's surface budget, meaning through an estimate of the radiative and the turbulent fluxes. There is the Earth's heat inventory, which is something I will discuss also in further detail. So providing information on where the heat is stored in the Earth system components, and the evaluation within climate models, helping to shape and further understand processes underlying the change of the Earth's energy imbalance, and coming back to be a central metric also to support the validation of climate model and projections. So I start with the Earth surface budget. So I will give a short insight on the Earth's surface budget. So this is an overview on the different major components for estimating the Earth's surface budget. So what you can see here are in red the outgoing parts, in yellow the incoming parts and reflected parts, and also you have precipitation and then evaporation, etc. So this is an estimate which has been done also under a study which was called NASA News, and provides an unconstrained view on how those different measurements have been derived from the available remote pool, let's say, of measurements like remote sensing measurements, in situ measurements, and atmospheric reanalysis and different approaches. So what you can see here is that with this you obtain an Earth's energy imbalance, which is rather high, but the point is, so this is just to discuss this. So this is the result of the NASA News, and you can see here that by using the derived estimates and trying to obtain an average estimate of this to derive in the end the Earth's energy imbalance, you get a value which is rather uncertain and ranges about 10 to 20 watt per meter square for value, which is ranging about 0.5 to 1 watt per meter square. So there had been different approaches in order to constrain this surface budget, aiming linked to this Earth energy imbalance. It's a rather complex approach, but these are some results. So added here are some values from different studies who have tackled this topic on the Earth surface budget, and providing different estimates also and adjustments for the different components and contributions through using an anchor of the estimate we obtained from other information on the Earth's energy imbalance. So there are still key issues for using the Earth surface budget for this specific question. So I would like to highlight that I'm just discussing here this for the specific question on the global Earth energy imbalance approach. So there's still a need to improve the uncertainty understanding of the 10 watt per meter square to 15 watt per meter square global surface energy balance residual. So to investigate further the surface energy budget at smaller and temporal and spatial scales, and to address specific accuracy and stability requirements linked to the observing system development and improvements, and also and recommendation which is provided for many new studies to go away from the global scale and to reach more the regional scale. So the approach of the region energy budget closure is a promising tool in order to move forward. So I would now like to go to my core topic. This is the Earth's heat inventory. So there is a statement we could have established through an international discussion group. We had this published in 2016, and it was a working group which existed over 5 years, from 2014 to 2019. And one of the statements was that the Earth's energy imbalance can be best estimated from the Earth's heat inventory, complemented by radiation measurements from space. And with the approach that the combination of multiple measurements and approaches is needed and is an optimal way in order to improve our estimates and to discuss the reduction of uncertainties, to provide observing system recommendations, and also to improve the climate synthesis and models. And that the recommendation is that progress can be best achieved with a concerted international export and multidisciplinary approach. I'm sorry. So what have we done in this study? So it's a study which has been sponsored by the Global Climate Observing System, GCOS, and with the aim to work with the different experts together and at international level, and to compare wherever possible the different estimates for the Earth's heat inventory, with tackling the specific question on where does the energy go. So what we have done here is to use the and provide a new assessment of the ocean heat content. So we have used 15 different products available internationally on estimating the ocean heat content. There had been a new estimate from the specific core group on the estimate for the storage over land, heat content over land. Also the same for the atmospheric heat content, and also for the heat available to melt the cryosphere. So what has been done here, for example, for land, there had been a new estimate provided for the borehole temperature profile measurement starting in the 60s and using global mean ground heat flux estimates, and providing us an estimate for the heat accumulated in the land component. There had been a group which was working on the atmospheric heat content by using a combining different methodologies. So we're using remote sensing data and radio sonde data, and also different reanalysis. So particularly they have used 4 different atmospheric reanalysis, and they have put all those information together in one reply to contribute to this Earth heat inventory discussion. And then there had been also a group working and basing on international activities on cryosphere estimates. So this is an estimate for the first time on where the heat available to transfer, it had been transferred in the heat available to melt the cryosphere, because previous estimates are mostly focused in terms of the large scale view on the mass loss. So, but here, for example, what you also consider and you do not consider, for example, for sea levels, are the contribution from sea ice as well, etc., and provided an overview on the different estimates. And again, here for specification we had on the glaciers, but further improvements can be done. So, and here is on the ocean heat content. I will spend a bit more time on the ocean heat content because I'm a physical oceanographer and it's my core expertise. So you must apologize that I be a bit longer here on the heat content. So as I said before, we have done an estimate and used 15 different international products. And what you see here is an ensemble mean in collaboration with all those many experts, and provided over different depth layers, and starting with the year 1916, and the shaded areas in different colors provide you an overview on how those different products differs at the different annual averages. So what is the baseline for this estimate? The baseline is an observing system, in situ ocean observing system for subsurface temperature, which is strongly dependent on the evolution of the technical capabilities, starting before the 50s, of course, but the major technical, or let's say, and also of going field work activities started with the 50s and 60s. So usually we start our estimates with the 60s. We had, at least for the Northern Hemisphere and some parts of the ocean, some tracks available which had been taken up regularly through shipboard measurements. And you can see these are the so-called XBT measurements. And you can see that there is also from the 60s up to the 80s a huge increase in the coverage of the data. And here you see an example on how those are deployed, and they are directly linked to the ship and directly with a small cable you can't see here, and directly transfer the data. But there had been a huge issue because there had been a bias which had been detected in this so-called XBT and MBT data. And so this makes up a large difference between the different estimates because different correction methodologies are proposed, albeit they made up the majority of the data before the year 2000. With the year 2000, The majority of the data is provided from this international Argo program. I have something here. So this is the international Argo program, the most recent area where we have a distribution of floats, which are covering a targeted area between 3 degrees and 6 degrees north and 6 degrees south. So this is an example of how this coverages look like, and this is increasing, and how you can see what is the coverage. What is the coverage in terms of international contribution to maintain this measurement of subsurface temperature and salinity from the surface down to 2000 meter depths. And this is just an example of how this works. If you're interested in more details, I've added this slide. I'm happy if someone is interested to provide more information, but it's working in a different cycle, and surfacing and then drifting for a couple of times, and then going down in order to provide a full depth measurement and directly transmitting the data to the satellite, which is then transmitted to a ground station and so on, so to provide this operation aspect. So what you can see here are differences. So you have these differences of this time series. So you can see on the left-hand side, again, a summary on the statistics of the observing system evolution. You can see here, for example, at depths that you have started to become data available, which are going below 700 meters depth, for example, only with the implementation of the Argo array in the early 2000s. And before that, the data coverage was particularly very sparse in the deeper area, and also that you have a huge asymmetry in southern here. So this poses challenges together with the instrumental bias I just mentioned before, which explains the difference between the time series. For example, here on the right-hand side, this is a publication from 2013, was also a community publication comparing different estimates. And you can see here that in the 50, 60, 70, 80, where you have these huge differences in data statistics, you have also an impact on the difference between the estimates. But all time series show a clear warming of the ocean, upper ocean. And then we have Argo, and albeit Argo is very huge, so coverage is really increasing. We still have huge differences. On the upper part, you see here an estimate of the rate of change. So this is how you estimate also the Earth's energy imbalance. You can see these are in different colors. You can see different products used, but they're all more or less based on the same data set, on the Argo data, but with different processing, and you still have a huge differences here between these different products. Albeit data coverage is really high. And this is maybe explained that we still have large gaps. So we are covering with Argo only 50%. Indeed, the area where you have the huge increase of warming, but nevertheless, the deep ocean is missing, and the polar areas and also marginal seas. And so what can we really expect from these regions? So there had been some estimates for the deep ocean. These are also regularly updated and are based on the sparse direct measurement, shiftboard measurements. And so they're rather uncertain and provided for these boxes, large areas, so that you can see here are shown highlighted in gray. But nevertheless, it's a measured estimate, and we can see that there is still warming. There is warming in the deep ocean, which is measured, albeit with huge uncertainties. And for the global scale, this is about 0.1 watt per meter square, which is for today is our best estimate we can get. And also this has been a study which has been done in 2013 and could show that we can have an error of about 10% if we do not consider areas in the shallow area for the estimate of global ocean heat content, which is quite huge. And there's another discussion on the, this is a study which has been done last year, and using a combination of observation and ocean reanalysis for the Arctic area, also amongst others, to understand the contribution of ocean warming for the global estimate. And the results show that there's about 4% estimate for the global scale contribution from the Arctic area. So there are different areas where we would really improve our estimate of the ocean heat content if we would increase the observing system. So this is the result, however, what you can get from these 15 different international in situ based products. And also there show some differences in spread, and particularly in the year-to-year variability and decadal variability. All in situ based products I'm sorry, show an increase in ocean warming over the past 5 decades at rates of 0.54 to 0.5 watt per meter square for the upper 700 or down to 2000 meter depths of a near global ocean between 60 degrees and 60 degrees north. And there's another interesting figure I would like to show, which was also the outcome of our heat inventory paper. So you can see here from the left to the right different colors, and these different colors are represented here for different depth areas, integration depth areas for ocean heat content. So the upper 300 meter, upper 700 meter, the upper 2000 meter, and 700 to 2000 meter depth, so more the intermediate layer. But you can, and then you have different estimates over which are going closer to times over the full period or the real close to the last 1.5 decade. What you can clearly see is that with the course of time that there is a redistribution of heat, in particular redistribution of heat into the deeper layers of the ocean. So this is one point, which is particularly clear if you look at the 700, 2000 meter depth layer, where you have a kind of propagation of heat into the deeper layers. And in addition, what you can also see that you have an increase of the spread, meaning that there is an increase of variability, albeit your observing system is much stronger. So this is a very strong result, and it's a really still very open question. So what have we done with all those estimates? We have estimated where the heat is going into the Earth system for the land, ocean, atmosphere, and cryosphere. This is the estimate we could obtain, a number of 358 for this period up to 2018, with a contribution of about 90% for the ocean, 5 to 6% for land, 3 to 4 for cryosphere, and 1 to 2 for the atmosphere, depending on the period. And this, if you take up the rate of change of this heat content in zeta-joule or in joule, you obtain an estimate of the Earth's energy imbalance. And we could obtain two values, 1971 to 2018 of about 0.5 watt per meter square, and an estimate for the last decade, which is showing a doubling of the Earth's energy imbalance. So why should we care about this? Why should we care about the precision of these small numbers, which could appear very small, between 0.5, 0.8, and so on? Because the Earth's energy imbalance is really providing a root cause of various facets of observed climate change. And this is, for example, something which has been demonstrated. So the positive Earth energy imbalance is responsible for warming of the land, with all its consequences, which had been assessed in the land report, special report in 2019 by IPCC, for example. The positive Earth energy imbalance is responsible for the warming of the atmosphere, which has been also, for example, in its consequences assessed in the 1.5 degree report, for example. Ocean warming, also assessed in SROC in the special report on ocean cryosphere, for example, and the loss of ice and its consequences. So the various facets and impacts of observed climate change arise due to the positive Earth energy imbalance, which thus represents a crucial measure of the rate of climate change. So what is the Earth's energy imbalance? Again, so the Earth's energy imbalance is the portion of the forcing that the Earth has not yet responded to. So it's really providing the information of what has stated by James Hansen is how much heat is still in the pipeline. So the Earth's energy imbalance is the most critical number defining the prospects for continued global warming and climate change. And so this simple number, the Earth's energy imbalance, is the most fundamental metric that the scientific community and public must be aware of as a measure of how well the world is doing in the task of bringing climate change under control. So there's some few slides I would like to finish, and which is leading you to some very open questions. So this is the combination of the radiation at the top of the atmosphere and the Earth's heat inventory. And this is done by the so-called budget constraint on the Earth's energy imbalance. So the change in the top of the atmosphere net radiation and the rate of global ocean heat storage from independent global climate observing systems should be in phase and of the same magnitude on annual and longer timescales. So all other forms of heat storage are factors of 10 smaller at that timescale. So you can see, for example, on the right-hand side, this empirical demonstration of this constraint I've just mentioned. So it is based on a climate model simulation in this paper from Palmer and McNeil. And they have provided correlation between the Earth's energy imbalance and the ocean heat storage. So they have used the full depth ocean heat storage. And on the lower part, you can see the trend lengths. So they have compared the correlation of the trends between both components in months here. And you can see if you start to become at a period of 1 year and longer, you can see that those are well correlated at different trend scales and variations. So this is one of the empirical quantification of this statement. So again, what can we do and what is possible to do in order to establish this budget constraint, given all these challenges I mentioned above, before, such as, for example, the challenge of the observing system. So we are often talking about this golden period for ocean heat content estimate and validation, or let's say for the Earth's energy imbalance budget constraint, which is driven by the strength of the global observing system, and particularly driven by the invention of Argo. So in the year 2005, the Argo program was reaching its initial target of near global coverage between 60 degrees north and south. And so this is the period where evaluation starts. So for example, on the lower left-hand side, you see a most recent study from Mercator, who's the principal investigator of the CIRRUS program for the net flux at TOA, and comparing or showing this Earth's energy imbalance budget constraint for in blue, the planetary heat uptake. So it's one estimate of heat content together with our estimates from the GCOS paper for the atmosphere, cryosphere, and land. Combined, you can see that there is a very beautiful correlation, and so that this budget constraint is really fulfilled from completely independent observing systems, together with the uncertainties, but the result is impressive. And the information here is also that heat has been sequestered down into deep ocean layers over the past 5 decades. So that's something I mentioned earlier. And the record values and also the record variability, which could be measured. And also the increase in the Earth's energy imbalance, so which has appeared to be doubled over the past decade. On this, there has recent new studies working on this. How and why did the Earth's energy change over the past decade? So Löb et al. Have constated there also the increase of 0.5 watt per meter square. So it's the current of what we have obtained. And their argument that there is a decrease, and decrease of reflection of energy back into space by clouds, and also effect of sea ice, and the increases in well-mixed greenhouse gases and water vapor. There's a study from Karina and al. They have used then the CIRRUS data and decomposition the different radiation components, and they argue that they have found also an increase in core independently, and they raise it to a combination of rising concentration of greenhouse gases and recent reductions in aerosol emissions. And there is another one, which is a reconstruction of the Earth's energy imbalance, combined with different methodologies, including the analysis systems. And they argue they have also found an increase, and that this is linked to the changes in surface heat fluxes, planetary heat redistribution, and changes in ocean heat storage. So there are still huge discussions. There's also some paleo evidence I would be keen to further discuss with this group, particularly to understand on whether we can learn something. There had been some papers who are linking changes in the Earth's energy imbalance linked to internal climate variability, such particularly ocean circulation. And I think there are still an open way to understand what's happening, and maybe combining paleo perspective with a recent perspective could bring new advances here to solve this enigma. So quickly on climate models, what is the current status? So this is an assessment, the first assessment done for the Earth heat inventory for CMAP 5, and it should be done also for CMAP 6. And you can see that there are still huge differences in terms of representing the Earth's heat inventory, and particularly with an overestimate of the ocean heat content and large uncertainties in the continental and cryosphere heat storages. And also a discussion which is updated regularly. I recommend for those who are interested on the surface budget from Martin White at ETH Zurich. And he just recently updated also the surface budget estimate for the CMAP 5 and also added information for CMAP 6 on this discussion. So some key messages, take-home messages before I'm happy to take many questions, I hope. So the key messages to go home are the Earth's energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. And understanding the changes in the Earth's energy flows helps understanding the main physical processes driving climate variability and change. And the Earth's energy imbalance itself is the most critical metric that the scientific community and public must be aware as a measure for prospect of continued global warming and climate change, and as a measure of how well the world is doing in the task of bringing climate change under control. And the Earth's energy imbalance has increased over the past decade, and drivers for this change of anthropogenic and natural origin need further evaluation. But this is a really urgent matter because it has doubled, and all this energy, which is already available for the change we have observed, the double is available in the Earth system now. So we need international collaboration to urgently understand this issue. Thank you very much.
Jackie or Ryan, do you want to deal with this question? People should just jump.
Yeah, anyone is free to ask a question, whether you can unmute yourself and just ask the question, or you can put it in the chat and either Jackie or I will read it.
So I have a question. This is Paul Falkowski. How does heat get so quickly into the deep ocean? I mean, I guess Dean Romish and Carl Wunsch wrote a paper about this almost 20 years ago. And it seems incredible to me that we can see these changes in the deep ocean across the world within 50 years.
So maybe I would like to have a refinement of your question. So what is the deep ocean for you? Because the changes which are so fast, I show here, are going up to intermediate depths. So where we can have many processes at hand, which could explain such a fast change. So for the very deep, deep ocean, we do not have yet evidence that there is a fast change taking place. Maybe you can precise.
Yeah, that's fine. I mean, I guess if I think about this, it's very difficult for me to understand the continuity of even intermediate waters being compatible with the circulation and the formation in the polar regions in the North Atlantic, for example, or the Antarctic. So how do we get these waters warmed in such a short period of time? That's the big question for me.
So it's yes. So I would like to highlight first that the change and I've shown is redistribution of heat. So I was really carefully choosing these words, and I was not talking about warming because that's the statement which is on a very, let's say, short time scale. But what we can, but we know also, and also where we can see this large variability, if you compare, for example, the Earth energy imbalance and the heat storage, is to see that these changes start with the year 2010, and this is the year when the so-called hiatus stopped. And there had been a lot of papers which are talking about heat distribution linked with climate variability, particularly ENSO in the tropical areas, which provide a gateway of fast heat transfer into the deeper ocean layers, deeper, I mean intermediate layers, and a redistribution of heat into the Antarctic polar very resurface. So this, what we see today, so this acceleration had been predicted in some papers on those timescales, for example, England et al. In 2014. So the gateway are the tropics here. Potentially, that's something, it's one of the pistes. Did I reply to your question?
Yeah, I have to, I'll read a little more. It's very unclear to me why, where this heat is coming from specifically in the first 1,000 meters of the ocean. I mean, it's very difficult to quantify these, obviously, but and I see your uncertainties, but it's amazing to me you can ascribe 90% or approximately 90% of the heat is maintained in the ocean, which is not that surprising, but it's surprising that it's maintained in such depth. So that's okay. I have to think.
I like this question. I will also think would be happy to reshed on this again. I have some more replies, but I would be happy to have a discussion on that. So a nice question to ask like this.
Karina, this is John Wilkin. Thank you for the talk. I enjoyed that. So I had a question about the ocean heat content trends. You pointed out that the variability in the estimates is actually greater more recently than earlier. And is that because previous heat content estimates were just overly optimistic in their error bars, or I don't see why. I'm perplexed that spread should be increasing when the observing network is definitely far more comprehensive now than it has been at any time. Do you have any insight on why this spread is emerging?
Yeah, so we are already discussing this and we are studying this, but what we can see in those periods is that there's increase of amplitude of variability, and which is taking place in different areas, so I cannot really locate. And also, there are also other issues in parallel. For example, the sea level budget doesn't close anymore in those periods, particularly to 2016. So there are still many questions open whether there is a problem in the observing system and whether we do not resolve some specific variability in some areas, and which is particularly strong during those periods and which lead to these huge differences between the different reprocessing products. And so the question is still open. I have no reply, but I'm not the only one who is observing this issue. And there are huge discussions about across many people. So,
do you think this might come down to the deep ocean again?
No.
Because we are seeing, no?
I don't think so, because this is really too fast for the really deep ocean. How would you explain this? Because they are really here, the upper 2,000 meter depths where we see larger. So we have the clear redistribution between 7 and 2,000 meter depths. But what are your thoughts on that?
The fact that, when you showed those, the heat flux residual estimates based on the different climatologies from Argo, so from Scripps and IPRC, really, they should at least agree with each other within their own error bars. So there's something there in the analysis approach that's either underestimating the errors or is introducing a bias, because they're starting with the exact same data from Argo, right? And we trust the data from Argo pretty well.
But here you are not looking at the joule, right? If you compare the time series, they agree well. Here you are looking at the rate of change. And that makes problems coming out far and makes a more picking on the variability. So if you do this, for example, reanalysis systems, it's impossible because the systems are not stable, and potentially our reprocessing are also not stable, right? Because we have many assumptions and we are not conserving. So something where it is working well in terms of the watt per meter square is, for example, reconstructions like ECHO, where you have really conservation of tracers and so on. So we are going really into different questions here, because we are looking at the rate of change. We're looking at the time derivative of ocean heat content and not at of heat content. And that makes it a bit more complex. So it's something to consider while tackling this question. Because you do not have the same result if you look at the heat content. So you see the spread is decreasing, so as you would expect, because the observing system is improving. So this is this figure here. But here is a different word, let's say.
Yeah.
I had a question about that slide you just took off, the series slide. Yeah. The last, since like 2013, the standard deviation that really fits the trend line pretty well. But prior to that, there were very large changes in the series from year to year. Is that instrumental kind of a thing, or is it had something to do with what we think is the real physics?
That's exactly. So I'm working with a PhD student exactly on this question. So we are still challenged. So I cannot give you a clear reply. It's not clear. But we are still, let's say this way, we are still working, and also coming back to the discussion I just had with John. We are still trying to really understand and to exclude any non-physical reasons for those changes, in order then to start to think of maybe physical change. But for the moment, we are not at this stage. So there are still many unclarities. Again, as I said, there are other cross checks you can do, for example, with the sea level budget. So you use altimetry from remote sensing, you use ocean mass information from remote sensing, and then you have another independent control, let's say, on what you are looking at your time series. And also this doesn't work. So there's also a problem. It's not closing. So we are a bit faced of kind of challenge during the past years.
Okay.
So I cannot reply to your question.
Thanks.
So I have a question, and maybe it's a naive question, but and it certainly relates to the issues of trying to determine what's happening regionally. But we often think of this change in energy balance as extra heat going into the ocean. But of course, what's happening is in low latitudes, heat goes into the ocean, and at high latitudes, heat comes out of the ocean. Are the data good enough to tell to what extent the change in stored energy is coming because less heat is coming out of the ocean?
So I think this is a question which is going to an analysis of the so-called CAGES approach or the regional budget approach. I think you would need to really understand the regional heat budgets to reply specifically to your question. So you need to understand how much heat is going into the specific area and how much heat is going out into the specific area in order to reply to your question. And the challenge here are the transports in the ocean and the transports in the atmosphere. So this is the real challenge of tackling research questions you're asking for. For some areas, this is already possible because you have validation measurements available, such, for example, for the ocean in the North Atlantic, because you can start to close the boxes and start this CAGE process. But this is something, for example, the CAGE process had been proposed by Mercator during the beginning of WOS in the 70s. So there's this paper and people try to do this, but they're still challenged. Another one, which is also very interesting, is the Arctic in this area, because there are new successful studies in terms of really understanding the flow of energy at a regional scale for the Arctic, because you also have their mooring, and then you can use validate, for example, resonance systems, and you can use this, etc. So yes, it's a very important question. And for some areas, I can reply yes to your question. There's ongoing, but for some areas, it's still not possible, like, for example, the Southern Ocean.
Yeah, and that was going to be my follow-up, because it seems like that would be a very difficult area. Are you aware of any new technologies or observational approaches that are going to help with the Southern Ocean?
Yes, of course, there are many. I will reply you with my core expertise, and this is for the ocean and the extension of Argo systems. So there are two challenges, for example, to extend the, let's say, automated observing system like Argo. The first one is to measure under ice. So there are new technologies under the way. Then, of course, there is a program of a deep Argo program. And so this is also starting, and there are already some tests going on, successful tests. And there's also the challenge of going closer to the shelf area so that the instrument can detect the change of bathymetry, right? Because today they're programmed to stay in the open ocean because you would avoid damage by going to crash on the coast. So there are also new technologies under the way in order to get closer to the coast. This will all help in order to go, for example, in the measuring of the Southern Ocean area to have an increase. And so, of course, but it's still a challenge for the other components like surface fluxes, etc. It's still a huge challenges and demand for measurements. Or did you have another specific component you wanted to ask for?
No, that answer was great. Thank you.
Mm-hmm.
So I have another naive question.
These are the most difficult ones.
Yes. So for many years, the major uncertainty in climate has been ascribed from several aspects to clouds and cloud albedo. And I know, you know this much better than I, but the atmospheric radiation measurements program is going on now for more than 2 decades. And as we transport heat, as Tony was mentioning, to the high latitudes, obviously cloudiness is going to change. So how well do we know the feedbacks between the transport of heat and, for example, the albedo of stratus clouds, which are sometimes at very high latitudes, very difficult to make measurements of, because we can't also differentiate that from skin temperature of the surface ocean or from ice. So I just, your thoughts.
Okay, so maybe just to say it's really out of my expertise. So it's just some thoughts which are based on readings and exchanges. But as you were stating, this is still a very open research area and challenged by measurements, challenged by uncertainties in the model, challenged by the methodologies. So I think this is a research area, still a way to go. But again, it's not my in-depth expertise. What are your thoughts on that?
Okay, thank you.
Karina, I have a related question. This is Rob Sherrill. Follow-up really to Tony's and Paul's. And I'm thinking mostly about Antarctic areas and Antarctic shelf regions, or at least the region that's seasonally sea ice covered. How important, if we're trying to explain these processes to especially general classes of students who are not scientists, how do we talk about the importance of albedo and absorption of solar energy as a somewhat independent process from heat transport that's just driven by conduction and the difference in temperature between the water and the air? Do you have any general thoughts on that? I mean, a situation where solar heating of the surface creates an energy flow into the ocean, whereas the conductive heat transport would go the other way. It's really a question, I guess, of how important is ocean albedo, but also solar radiation, given the change in the hydrologic cycle. And, you would expect that polar regions would become more cloudy in the coming years. Have any general comments on how we talk about sort of albedo and solar radiation uptake as opposed to heat transport by temperature difference?
So potentially, if it would be, maybe I will give you a reply in the context of a changing environment. So in terms of the climate system and climate change. And so these specific examples may be a good point for representing this and going into detail then on all these aspects you were mentioning. Could be maybe the feedback mechanisms which are very critical in terms of discussing on climate change and its implications, unprecedented change. And in this context, when you were saying this linking to the heat uptake and the change in heat uptake could be the linkage of warming in terms of reduced sea ice extent, which in turn gives you a change in the surface radiance and an increased uptake of heat of the ocean, so which in turn leads back to a warming, increased warming of this area. So the amplification, you can observe also an impact in terms of the seasonal cycle. So you also have a change in the seasonal cycle. So I think that would be a very interesting in terms of knowledge transfer, and something I think we do not consider enough and we should consider more, and also in our understanding is the change of the seasonal cycle. So we take off all the time in our analysis because we look at net anomalies. And so these two aspects will provide then increased warming, and this feeds back again into an increased melt of sea ice, etc. So that could be one example on guiding and having a storyline in order to provide then more details. So could be maybe a nice way of transferring knowledge to younger people. That could be an aspect of climate change, very with a nice example.
Can I ask a question? You mentioned one of the longer term variations that affects this is the PDO. Is there really such a thing?
Do you ask me the question of the PDO exists or not?
Yeah, yes.
So I think we can maybe discuss on how you want to call it, but different climate variabilities which exist and taking place in the Pacific Ocean in a repeated manner at specific timescales, so they are defined somehow. Of course, they exist. But then you can go further and ask this more general question on why do those different climate variability patterns exist, like ENSO, and what determines periodicity, what determines the change of those appearances, etc. So this is a reply to your question. Very general one.
Well,
I don't know where you want to go. Bring me on the journey.
Well, El Nino and so I think it's pretty well understood, and there's been many El Ninos and La Ninas, and we have good data on it. But the PDO seems more like a statistical abstraction. I'm wondering if there's something really physical about it, that have there been enough of them to really get good data to say that that's a thing, or is it just some sort of index?
So I cannot reply you from an atmospheric point of view, but I can reply you from an ocean point of view. And there is a broad coverage, in particular for the physical parameters and the description of the impacts of the PDO and also the patterns of the PDO. So they are clearly defined, and a lot of physical mechanisms. But it's true that there are a lot of papers which are also talking about different aspects and different namings of the Pacific Decadal Oscillation. So I'm not an in-depth expert, but I think there is a good evidence in terms of the Pacific Decadal Oscillation from an ocean perspective. So, but again, I cannot reply from the atmospheric perspective.
Thanks.
Any further questions? I can't hear you. Yeah, you're muted.
Yeah, you're unmute.
Sorry, I was asking if anyone has any question. Karina, I said I'll talk to you again another time. I don't want to keep anyone. I do want to follow up.
Me
Well,
too. But I really appreciate a lot this question. It's really nice. And yeah, thank you very much.
Well, maybe sometime in the future we can have you in person here. But I think for now, it's really, thank you so much. So if
No, thank you all.
no one has any question, I know Karina has to put the kids very soon, feed them and everything. So we'll say bonsoir and au revoir.
Thank you for the seminar.
Thank you.
Thank you for.
Okay, bye, Karina.
Bye.